By the 1970s, they had finally outpaced the weather. Now scientists were able to move on to their greatest challenge, predicting the climate years into the future. Climate modelling had finally come of age. It was in the nick of time. In the 1960s, researchers had revealed that pollution was raising carbon dioxide levels in the atmosphere. They knew that carbon dioxide was a greenhouse gas, which should warm the planet up. But how much? This was the first big test for the climate modellers. They started with a simple question. What would happen to the Earth's climate if carbon dioxide levels in the atmosphere were to double? So the modellers turned to their computerised climates. They doubled the level of carbon dioxide in their model atmospheres, and they pressed go. So just how would the world's climate change? The models churned through thousands of equations that simulated the climate system, from cycles of rain and snow on land to sea ice around the poles. And they calculated what effect the extra carbon dioxide would have. The result was surprising. The models suggested that a doubling of carbon dioxide would warm the planet by about 3 degrees. It may not sound like much, but the last time the world was that warm, melting ice meant that large parts of London would have been underwater. By the late 80s, the model predictions had helped turn global warming into a major political issue.
The danger of global warming is as yet unseen, but real enough for us to make changes and sacrifices so that we do not live at the expense of future generations.
But the predictions also fueled a backlash. In the 1990s, the whole idea of global warming came under attack, and the models were a prime target. Critics said they were just too simplistic, little better than computerised crystal ball gazing.
Global climate models are simply not yet sophisticated enough to include all of the physical factors that make up the climate. Policymakers have started asking themselves, why should we rely on such primitive models?
I don't think we could speak of the models as being accurate at this point. They're experimental tools. I don't know why they're taking the models seriously.
The critics had a point. The models were struggling to cope with the complexity of the Earth's climate system, and they were still unproven.
The problem was that the models predicted so far into the future, it was impossible to tell if they worked. What the modelers needed was an event, something big, something immediate, something to test their mettle against.
They finally got their chance in June 1991.
Mount Pinatubo volcano has erupted, throwing rocks and molten lava miles into the air. Hundreds of thousands of people have fled their homes, but there are no immediate...
It was one of the largest and most violent eruptions of the 20th century. Millions of tons of debris and gases were thrown into the air. For Jim Hansen, one of the world's top climate modellers, it was the chance he'd been waiting for. Finally, he could test his model. He knew that the Pinatubo eruption was so big, it might well have an effect on global temperatures. Huge volcanic eruptions on this scale can cool the climate because they send a cloud of dust and gases into the upper atmosphere, which reflect the sun's rays back into space. The question was, could his model accurately predict Pinatubo's cooling effect on the climate over the next few years? If it could, then his predictions about global warming would have much greater credibility. Meetings were summoned, data was inputted, and the model was run. It came up with 3 predictions. First, it said that the global climate would cool by 0.5 degree. It also said that this cooling would last a couple of years. And finally, it suggested that the regions that would feel it most would include Europe and the USA.
Now, after all that furious activity, all they had to do was sit back and wait.
As the temperature records came in from around the world, Hansen could afford to smile.
All around the country, people are talking about the wild weather this summer. And in a lot of places, what they're saying is, maybe it's cold outside.
Cold it was. In fact, around the world, the 2 years following the Pinatubo eruption were indeed 0.5 degree cooler. And the places that suffered most included the US and southern Europe. Hansen's model was spot on.
This was a huge triumph for the modellers. It proved that in terms of the big picture, models could accurately see the future. This wasn't science fiction, it was science fact.
The climate modellers had been vindicated. And by the late 1990s, climate models had gained the respect of scientists around the world. This is what a global climate model produces, a map of the Earth in which the colours show how climate changes as carbon dioxide levels rise. In this case, we're looking at temperature, and you can see by the changing shades of the warmer tones, the yellows, the oranges and the reds, that there's quite a bit of variation. But down here in the corner, that's the average temperature of the globe. And it's thanks to models like this that we've got a good idea of what global warming will mean for the planet as a whole. The models give a range of predictions, but overall the message is consistent. If we doubled the level of carbon dioxide in the atmosphere, the Earth will gradually warm by around 3 degrees, pretty much what they were saying 30 years ago. These models also give us a broad idea about regional changes. For example, you can see that the Arctic warms much more than the equator. You can also see changes at an even finer scale, because in this model it looks like Britain and Ireland warm much less than our continental neighbours. But if you want to zoom in for even more detail, it just isn't there. These models struggle to give us what we really want. Information about what's likely to happen right on our doorstep. Powerful as they are, computer models are still wrestling with the complexity of the climate system. One of the key challenges is scale. Even today, the models can't take into account all the local small-scale processes that happen across the planet. More computer power will help, but that alone isn't enough. Sometimes there's just no substitute for some proper field research. I've come to Greenland to see how scientists are working to fill the local gaps in the model's calculations. Because to accurately predict the future, modellers need to understand what's happening on the ground now. More than 80% of Greenland is covered in a huge ice sheet. Outside Antarctica, this is the largest body of ice on the planet. And one of the biggest unknowns about global warming is how this ice sheet is responding to rising temperatures. Climatologist Connie Steffen has taken me to a glacier that he's visited often. It's one of many glaciers that flow from the ice sheet down to the sea. When Connie first came here, the surface of the ice was smooth and gently sloping. It was known as the Dead Glacier.
That glacier was an old name because the glacier didn't move for a long time.
Right. And have you up there before?
We had actually a station. We put up a station on that glacier in '97.